Okay, so y'all know the drill. As always, don't incriminate yourself. This will be on YouTube. Okay, so the TAs from previous semesters they've prepared an exam review similar to the one we had last time. I'm gonna go ahead and paste that into the chat. Uh, so somebody let me know if you can open that up. When I publish this as a YouTube video, I'm gonna put this like in the comments or something. So you need access. You can't get access. Okay. Hmm. See, we've got Andrew here. Andrew, do you know did I mess up or
Oh, let me look.
okay,
Well,
yeah, because I don't have the text ag link. Um, do you
I can
think
just paste. I remember what it is. Hold on, let me.
yeah, please do. I would appreciate it. So y'all if I'm like going over stuff and y'all have questions that I can't answer, Andrew is not he doesn't have to be here. He's here because he loves it. So ask him your questions in chat. He'll be able to help you out. Um, he knows his stuff. Okay, so this you'll have access to? Okay. Cool,
I
cool.
think okay. He said it works. Cool.
All right, right on.
I can't promise I'll be here for 2 hours, but I'll stay around for a little while, I think.
Yeah. It's his time is extra, so y'all appreciate it while you can. Okay, I'm gonna go ahead and share my screen and let's take a look at this review. Y'all can see my screen, correct? Okay. Somebody give me like a yes or a no.
Yeah, I can see it.
Okay, thank you. Okay, so here's the topics for exam two. What's going to be on the test? We've got linked lists. So this is not going to be like, super theoretical stuff in the sense that it's like, linked lists are pretty simple, but it'll be, more based on do you know how to implement a linked list or do you know like what the time complexity of a linked list implementation would be? So as an abstract data type, a linked list can be converted into different data types. So using a linked list, you can make a stack, you can make a queue, you can implement different operations. So long as you know generally like what the time complexity of operations are, it's mostly questions about how you would implement a linked list. Um, for the programming assignment, y'all need to be comfortable using linked lists to access like, the next node, so on and so forth. If you've done PA3, should have a head start on this. Um, Someone made this bullet point here, templates instantiated at compile time. I don't think that belongs under linked list, but this will definitely be on the test. So cough cough, y'all need to know that. Like the compiler handles templates. It's not done during runtime. We're going to be talking about binary search trees. So there's a lot to cover here. This is definitely the bulk of the material. So there's going to be some basic vocab, which you'll probably have picked up already. We've got tree traversal. And within tree traversal, I'm going to spend some time talking about postfix, infix, expression trees, so on and so forth. We're going to talk about like PA4 type stuff, so inserting, removing from a binary search tree, what the complexity, the cost for those things are. We're going to talk about how that changes with a balanced versus unbalanced tree. Again, number of comparisons should be in that same vein. So everything you need to know about binary search trees. And we're going to wrap up with balancing trees. So like what is the definition of an AVL tree? How can you tell if a tree is AVL? How do you compute balance factor? How do you build an AVL tree? What is a 2-4 tree? Terminology for a 2-4 tree, red-black tree, so on and so forth. So we're going to have plenty of time to go over examples. This is just kind of the roadmap. And I think the Dr. Andrew posted, y'all should be looking at this, I think. So yeah, all of these PowerPoints, they're all real good. Okay, so from the questions we took at the beginning, we want to cover recurrence relations, Master's theorem, and balancing. Did I miss anything? I think that was that was what y'all agreed on. Okay, so I'm gonna go ahead and connect to my iPad. Uh, so y'all can see this, right? Can I get a yes or no?
Yeah, we can see it.
Okay, thank you. Okay, so recursion, let's start with that. So uh, recursion by definition is just any definition that calls itself. So It's a definition that references itself. So if you ask me what is recursion and I respond with recursion is recursion, I've answered you recursively. In a more formal mathematical sense, if you define some function to be a function of itself, so for instance, like this is a recursive function. And specifically, when we define recursive functions, generally what we're going to be looking at is we're going to have some kind of general formula, and we're going to have some type of base case, right? So it could be anything. Okay, so yeah, usually when we're looking at recursion, we're going to have these two things defined. So some common recursive algorithms that you might see, there's obviously simple ones like recursively print a list or recursively find the maximum element. I think for this test, probably the most important recurrence relations that you're going to see are the sorting ones. Also maybe Fibonacci. So if we were to define a recursive algorithm, so let's call this fib, and let's take some input in. We have to do these two things in order to define a recursive algorithm in code. So we have to come up with like what is the general recursive case and what is the base case going to be. So the base case for the Fibonacci sequence, let's say if n is equal to or less than 1, so let's say less than equal to 1, return 1, and then else return, and then so this was your base case, and then this is going to be your recursive case. Let's say return fib of n minus 1 plus fib of n minus 2. Okay. And so what we've done here is we have essentially taken the Fibonacci sequence and defined it recursively. And if we were to operationalize the time complexity of an algorithm like this, that would be like saying the time, and T here stands for time, the time complexity of this algorithm, which in this case is the Fibonacci sequence, is equal to the time that it takes for this to happen, which is going to be T of n minus 1, plus the time that it takes for this to happen, so T of n minus 2. And so this is kind of our general formula. So this is our general recursive formula. And then we can say T of 1 is equal to, what would it be? 1, I think, right? I guess you could also say T of 0 is equal to 1. That might be splitting hairs because it's what, 1, 1, 2, 3, 5, 8, so on and so forth. So I'm calling this like T of 0, T of 1, T of 2. And as you can see, if we plug numbers into this function, we do get the correct output. So if we were to call, for instance, fib of 4, this is going to in turn be the sum of fib 3 and fib 2, which this is going to be the sum of fib 2 and fib 1, and this will be fib 1 and fib 0. So you can kind of see where I'm going with this. So this is going to give you what? 1 and 1. It's going to give you 1. I don't think there will be anything here. And this will give you 1 and 1. And as you can see, we can essentially prove things about this tree by looking at the height. So if I were to replace these function calls with the actual numbers that they stand for, we can quickly see that this is going to be a 2 to the power of n complexity algorithm. And sorry if I'm moving really, really fast. The point that I'm trying to make I haven't made yet. So if we were going to do something like this, and actually draw out the cases themselves. Let's see, 2, 1, Someone have a question? So as you can see, we can kind of make an assumption about how good this algorithm is by drawing out a tree that represents all of the calls that happen. As you can see, this is relatively kind of O of 2 to the power of n, kind of relatively. So again, sorry to have blown through this example, but when it comes to recursion, there are some important things to remember. So you've got a general formula and you've got a base case. This is just an example of that happening. You've got your base case here and then your general formula here. You can operationalize that either as a system of equations, which is what this is, and you could actually try to solve for this term, or you could draw out the recursive call and try to solve this way. So this would be like the math method for solving a recurrence relation, and this would be the tree method. Okay, so y'all probably don't need to know Fibonacci for the test. This is just an example. One thing that you will need to know is merge sort. So merge sort. So let's assume that I've got like a list of numbers or something. So 9, 1, 2, 5, 8, 4, 6. Are these acceptable numbers? I think these are good numbers. Essentially, merge sort is going to work by splitting this up into lists until you get to the lowest level possible. And let's just draw this out real quick. So you get this. So merge sort splits everything to the atomic level to where the list cannot be split any further. And then once you've gotten to lists of size 1, you combine them back together. So that's going to look like this. So this will be 1 and 9. This will be 2 and 5. And you're doing comparisons at this level to sort these little sublists. And then at this level, you're going to do 4 comparisons, right? You're going to compare 1 against 2. You're going to compare 2 against 9. Going to compare 5 against 9. And then you add 9. Same thing here. 4, 6, 7, 8. And then finally, you'll do n comparisons on the last level. 1, 2, 4, 5, 7, 6, 8. Okay, did I lose anybody? Everybody comfortable? Merge sort?
What if there's like maybe one more element or like an uneven amount?
Good
Like,
question.
do you
Good
divide
question.
it based on the floor or something?
Yeah, so if there's an uneven amount, like if there was an extra element here, then we would have had to have broken this into, this would be like 6, 7, 0, and then 7, 0. So it would have just been a mess. So for the sake of having a clean example, I made it an exact power of 2. The only difference would be that it would take one more iteration to get from this step, and then there would be like another step here in the middle. I just, for the sake of like, I'm just like trying to show how to prove this. I don't actually want to get in the weeds. If you want to get in the weeds, by all means, go for it. Excellent question though. Okay, so this is like the skeleton of how merge sort works. And to prove the time complexity, like I set up here, there's kind of like the math method, and then there's kind of like the tree method. I'm just going to run over what these are really quickly. So let's do the math method first. Oh, oops. This is a good thing I'm not like an English major. Messing up my words. Okay, so for the math method, like I said, up here, we've got to come up with some kind of general case and some kind of base case. So for merge sort, generally, we're going to be splitting the problem into 2 subproblems that are each half the size. And we're going to be doing n comparisons per level. And we're going to stop. We're going to say that the base case, like we don't have to do any comparisons once we've got to this level in which every number is in a list by itself. So with that in mind, let's go ahead and come up with our formula. So 2 plus O of n. Okay, so y'all have probably seen this formula before. Is anybody unclear as to what this means? I kind of just described it a little bit in English. You know, I'm gonna label these things. So our formula that we just made, we just formalized this time complexity. This is the number of subproblems. This is the size of input to a subproblem. This is going to be the time complexity of one recursive step. Okay, so maybe before I move on, let me give you all some examples with different numbers here to kind of give you some intuition of what this really means. So if we defined a recursive formula that was like this, you know, something wacky, n over 10 plus O of n squared. If we define something like this, that's like saying for each recursive problem, we're going to have 3 subproblems, which is this, and it's going to be, they're each going to be a 10th the size. And at every level, we're going to do O of n squared operations, right? Or if we defined it to be like this, t of n is equal to 4 times t of n over 2 plus O of log n, right? These are just arbitrary numbers. That's like saying that our recursive problem splits into 4 problems, and they're each half the size. So it'll look like this. And at each level, we're going to be doing O of log n operations. So really, these numbers can be whatever you want them to be. But for our case, we're looking at this. So merge sort is going to break into 2 subproblems. The size of each subproblem is half the size, and the time complexity of one recursive step is O of n. So I'm going to go ahead and rewrite this down here. So t of n is equal to 2 t of n minus 2 plus O of n. Okay, and so this is not the kind of thing that I want y'all to memorize. I want y'all to understand it, right? Because if you understand what these coefficients and these terms mean, then you don't have to understand it, right? Because if you're looking at a problem that's like this, well, you can see, oh, of course, we've got 4 subproblems. Each subproblem is half the size. This is not something that you need to commit to memory if you understand it. So here's our general formula, kind of. Here's like our general case. And then our base case, we said once a list has one element, no sorting needs to be done on it because a list of one element is sorted. So this is our base case. So there's 2 ways that you can solve the merge sort recurrence relation. You can either draw the tree. So you can say, okay, I'm going to start with some array. And then this array is going to be broken down into subarrays. And as you draw out this tree, you're going to see the like geometrical shape of the tree start to appear. So you're going to see, okay, well, I've got so many levels and I've got so much cost per level. And so the tree proof is, I think, the easier proof to do. So merge sort is going to look something like this. And you can say, okay, well, to get from this level to this level, I have to do all of these comparisons, right? Like I've got to compare this element and this element. I've got to compare these. And eventually you figure out that to get from, say, this level to this level, or any level to any level, you're going to be doing O of n comparisons. And so on this tree, this is what, t of 8 elements I think I drew. To get from levels to levels is going to happen 3 times. So you're going to do O of n comparisons here. You're going to do O of n comparisons here. And you're going to do O of n comparisons here. And then the tree method is super cool because if you can visually prove, oh, well, I guess I've got 3 times O of n, 3 seems to be log base 2 of 8. I can take the cost for each level and just multiply that by the number of levels, and I get my time complexity. So the tree proof here is going to be like total runtime is equal to number of levels times cost per level. And I know that's not the most rigorous formula ever, but I think that's fair in plain English, right? Like if we can say each level is so expensive and we have so many levels, then our total runtime is just however many levels we have times how expensive each level is, which in this case, because we keep splitting the list in half, the height of the tree is going to be log base 2 of n, or at least close to that. So say height of the tree is relatively log n. It's close. So the number of levels is going to be log n, and then the cost per level is going to be O of n. So therefore the total runtime is going to be O of n log n. And this matches what y'all have been told, right? So, y'all know the lower bound theorem, like a comparison-based sorting algorithm. Its worst case will be no better than this. I mean, this does check out. For the sake of the test, I think y'all do need to remember that merge sort is comparison-based. It's a good comparison-based algorithm, but comparison-based nonetheless. So back to the math method. I accidentally did the tree method first, so this is the tree method. You can see the tree method kind of makes the math method a little bit easier to understand, right? So when I said we got two subproblems, that would be like, 1, 2 subproblems. Each input to the recursive case is half the size, so half the size here, half the size here, and then O of n per recursive step is just going to be how many comparisons need to happen to get from one level to the next, right? So if we had like 0, 4, 7, 9, 1, 2, 6, 8. To get from one level to the next, it's going to be O of n comparisons, right? Because we have to do 1, 2, 3, 4, and y'all get the point. Yeah, so y'all get the point. Briefly, I'm gonna touch over how you would solve the math method. So if you have the actual formula for the math method, which is this, and you've got the base case, which is this. It's basically a speed run of how do I turn this case into the base case. Semantically, that makes sense by saying like, okay, well, I've got this recursion that keeps happening. How do I know when the recursive step reaches this base case? So that's kind of our motivation here. And the way that we do that is we start solving for these terms, right? So if t of n is equal to whatever this is, we can plug anything we want in here as n. So, oops, my bad. So t of n over 2 is going to be equal to 2t n over 4 plus O of n over 2, which is going to equal 2, oops, my bad, y'all, 2 tn over 4 plus half O of n. And then we can plug this back into our formula over here and rewrite it to say t of n is equal to 2 times this mess, 2t of n 4 half O of n. And as you can see, when we simplify this, we end up getting this result. And as you can see, there's some patterns that start to form, so we can eventually rewrite this very generally and say that 2 to the k t of n over 2 to the k plus 2 to the k of n is what our formula is going to look like. And then essentially it's a comparison. When does this become this base case, right? And that's like saying when does n over 2 to the k equal 1? And this happens when n is equal to 2 to the k, or when k is equal to log base 2 of n. And then we just plug that in down here. So we've got what? 2 to the log base 2 of n times t of 1, which we said this was 0, so this whole term is nothing. And then plus, oh wait, no, this is k. It's K right here. It's K of n, and we said K was log of n. Okay, so that's the math method. This is a solid chunk of the test, like not this proof, like y'all don't need to know all this crap. So if you've sat here listening to this, thank you. What y'all need to know really thoroughly is like given a recurrence relation, you are generally going to have like a general formula and a base case. That's going to be apparent in the algorithm as like usually some kind of if statement that is your base case and some kind of else statement that is your recurrence case. You could formalize a recurrence relation by writing out what this recursive case is as a formula. In this sense, it's usually done with t, like t of something. You can solve either using this tree method or by using the math method. Merge sort is something important y'all are going to need to know for this test. I don't think you'll have to do it by hand like this, but you should at least be able to be comfortable saying like, given this formula, I'm looking at two subproblems. Each subproblem is size n over 2, and then it takes O of n complexity per step. And I kind of explain that with these examples. It could be any wacky coefficient that you could possibly think of. In the case of merge sort, the tree method kind of makes it like more obvious what those coefficients actually stand for. And you can solve either by like kind of geometrically finding the size of this thing, which is kind of O of n log n, or if you're determined to do this is the math method here. If you're determined to do the math method, then you can essentially rearrange terms and solve this top equation such that you reach the base case, and that's done in this way. Usually you're going to rewrite your general case in terms of k, and then plug your base case, and as you can see, you get the same answer. So that was these two proofs. Also exists the master method. So sorry to whoever's question this was. Sorry to make you wait for so long. The master method is going to take a formula like the one that we just saw, and let's replace these coefficients with variables just for our sake. O of n to the d. So the formula that we were looking at before, which was this one, where I said this is just vaguely kind of your number of subproblems, vaguely size of input, vaguely expense for one step. We can actually replace those terms with these variables, and maybe that is a more maybe that's a more elegant way of saying that this could just be anything, this could just be anything, and this could just be anything. The master method essentially takes this case and it says T of n belongs to one of three categories based on the relationships between these variables. And I don't think y'all need to memorize this. I really don't. But you're either going to evaluate your recurrence relation to be one of these three things based on A and B. So if A is less than B to the power of D, A is equal to B to the power of D, or A is greater than B to the power of D, you're going to get different answers. So specifically, if A is less than B to the power of D, you're looking at O of n to the power of D. Otherwise, if they're equal, it's n to the n to the power of D log n, and otherwise it's n to the log base B of A, I think. I think I got that right. Again, I don't think you'll need to memorize this. What you do need to memorize is like when the master method is applicable. So if you can rewrite your recurrence relation as something that looks like this, like if you can get a reasonable A, if you can get a reasonable B and a reasonable D, then you can skip all of this nasty nonsense that we just did up here and just very quickly solve these things. So in the case of merge sort, remember merge sort was this plus O of n. So our coefficients here, A is going to be 2, B is going to be 2, and D is going to be 1, I think, right? So we're looking at A versus B to the power of D. And in this case, we're looking at 2 versus 2 to the power of 1. We can see that they are equal, which means the time complexity here is going to be O to the power of D log n. So O to the power of, no, it's O to the power of n to the d. Oh, it's O of n to the power of d log n. Sorry, I tripped on my tongue so badly. So O of n to the power of d log of n. And as you can see, this is the third time that we've proved that merge sort is n log n. So if you get to the test, there's one thing you should know, that this is the case. So for the master method, or master theorem, I think is a better way to describe what this is. So for the master theorem, you have to be able to write your recursive term in this way. So if your recursive term does not have division in it, you cannot use the master theorem, right? So for quick sort, worst case, so quick sort, hopefully y'all remember this. The worst case is, I think, when you just pivot around one element. So that's t of n minus 1 plus t of 1 plus O of n. The master theorem does not apply here, right? Because you didn't write this as n over b, you wrote it as n minus something. So master theorem, theorem, without, can't use it. Okay, while we're on this topic, quick sort is like, if you have some random list of numbers, like we had last time, essentially you just randomly pick some kind of pivot point, which I guess I'm going to say in this case is going to be, I'm just going to pick maybe the first element. If you randomly pivot around this element, you're going to have a list of everything that is less than 9, a list of everything that is greater than 9. And based on where you pick this pivot point, you're either going to have something that looks like this, like a list, and you break it in half, kind of like merge sort, so on and so forth. This is going to be both best and average case, and it's going to be O of n log n, or you're going to just take the tail end off each time, which this is the non-ideal case, right? And then this will just happen forever, and then this is going to be O of n squared, and this is the worst case. So I do think you have to have these things memorized, what these cases are. I don't think they're going to ask you to, actually do quick sort by hand, but, just generally be familiar with these things. Okay. So hopefully that answers the person who wanted to talk about recursion. Hopefully that answers the person who wanted to talk about the master theorem and proofs and such. Okay. So any questions? And by the way, I can't see chat, so you're gonna have to unmute yourself.
Can you go over like postfix, like prefix, like doing like that form where you're given an equation and then you have to put it into a tree?
Yes. Actually, it is very convenient timing. Okay. Let's see. So there are a few different ways that you can think of postfix and infix, and where is it? Okay, so y'all should have access to this slide deck made by Sophia, and this one is good. This is like some of the best resources you're gonna find for postfix and infix. So I think this is really sharp. Okay, so infix notation is what you're used to seeing in math classes. Humans think in terms of infix. So if you see an equation like 8 divided by 4 minus 2 right away, a human can just tell you what that means. Postfix is like garbage that a computer would process. I don't agree with this meme here. Average postfix enjoyer. Yeah, whatever. So anyways, as a computer scientist, it is often our task to, bridge that gap between what humans are comfortable with and what computers are comfortable with. And so for this test, we're asking you to go from infix to postfix and vice versa. So essentially, there are two ways to do this. So I'm going to show you Sophia's way, which is on these slides. If that's more comfortable for you, go back over these slides, figure it out yourself. I personally don't like this. I do not like the stack and queue method. I like the expression tree method, which I will show by hand. But essentially, to go from infix to postfix, you define the priority of operands from least to greatest, And as you can see, this is what that ordering looks like. Not going to read that because there's an example right here. And so essentially you have a stack that is going to, where'd my mouse go? You have a stack that is going to store your operators as you traverse through this expression, and then you're going to have a queue that stores your expression as you go. So as you can see, we're going to be putting our operators on the stack until they're ready to be put into the queue, and then by the end of this traversal, our equation will be sitting here nicely in the queue. So first thing we're looking at is A. We push in first, I guess. So we look at A, and then we've got an operator, so we put that on the operator stack. We push B, and then something interesting is going to happen because this plus sign that we're about to run into has got lower priority than the multiplication sign. When you have a case where you've got something lower priority, you're first going to pop off of the stack, put it in the queue to make room for the lower priority thing. So that should be formalized here. So you're going to actually be putting what was on the stack into the queue because of the difference in priorities here. And then same thing, you're going to continue operands go to the postfix queue and the operators go to the stack. Let's just keep doing that. And as you can see, we didn't have an issue here because you can think the parentheses kind of like resets the stack, and you can think like, okay, well, division is more important than multiplication. This goes in like, PEMDAS order, whatever it is. And then once you reach the last operand, you now just pop off the stack and return to the end of the queue. And boom, this is your postfix right here. This is your postfix notation. And so as you can see, we've got postfixes A, B, star, C, D, E, and I'm writing this down because I'm going to do this example by hand. I'm going to show you the tree method. So it looks like that. And I will say going from infix to postfix is significantly harder than going from postfix to infix, or in this case, Sophia shows postfix to number. So you can evaluate postfix by like evaluating each step. So in this case, you've just got a stack. So infix to postfix, you need a stack and a queue. Postfix to infix, you just need a stack. And essentially the idea here is you push things to the stack. So you're going to push 5, -2. When you hit an operand, you apply it to the top 2 elements of the stack and then you keep going. So that's going to look like, what? Yeah, so that's going to look like this. So we push 5, we push -2. When we run into the operand, we are going to apply it to the top 2 things of the stack and then push that result back onto the stack. So we're going to do 5 times -2, and we're going to get a -10 on the stack. Thank you, Thanos. Yeah, cool. One important thing to note, and let me back up here, is that when you actually are applying these operators to whatever is on the top of the stack, you treat this as the left term and this as the right term. Right, so this isn't important for multiplication because it's commutative, right? But if we're looking at subtraction and we need to apply this to the stack and then push the result back to the stack, you are going to consider this to be the left term and this to be the right term. So really what we did was 5 times 2 in that order, and that is important. So like we had before, it's going to be -10. We're going to push -7, push 40, push 8. We run into an operator, so we're going to apply that to the top 2 elements of the stack and then push the result. So like I said before, it's going to be 40 divided by 8. And that in that order, it's pretty important. So that's going to give us 5, and we're going to push 5 back onto the stack, which is here. And then now we run into the subtraction operator. So -7 minus 5. Remember, order is important. So -7 minus 5 is -12. And then we're going to do addition, so -10 plus -12, -22. So that gives you that. So here's what I like. I like the expression tree. I think hit y'all with the fluoride stare for a second. Yeah, so the expression tree I think is a lot more foolproof, specifically because you can make you can make a mistake using this stack, or in the previous one, the stack and queue method. You can make a mistake and not know where you made it. And when you're looking over your work, you're not going to like immediately see something wrong. Whereas an expression tree, you can see everything laid out all at once. And I think it is a really nice safeguard from getting the wrong answer. So when I solve these types of problems, I use the expression tree. I recommend you do the same. Okay, so to go from postfix to an expression tree, so this is an important skill for my method. So pay attention to this. Essentially, you start at the end of the postfix expression, and when you hit an operator, you fill to the right, and when you hit an operand, you fill to the left. So as you can see, we start with addition. When we run into subtraction, we're going to fill to the right. We run into division, we're going to fill to the right again. We get it E, so we have to fill like this.
पैसा ऐड ऑन किया है ऊपर एक सेकंड हमें आलू का जो
If someone is asking a question, I can't make out what you're saying. Sorry about that. So again, you just keep filling in this tree until this should be a multiplication symbol, I think. Am I tripping? I'm not tripping. This should be multiplication. And then you fill in the tree like this. And then now you've got your wonderful expression tree. So in a second, I'm going to go back and cover more about how you would actually do tree traversal. But if you convert postfix to an expression tree, or if you convert infix to an expression tree, now you can flawlessly and effortlessly go between one and the other, and also see the proof that it's correct right in front of you. Very hard to make a mistake when you have an expression tree. Okay, so time for me to do this example actually in front of y'all. So let's see. So y'all can see my iPad again, right? Somebody please say yes, because I can't see comments.
Yeah.
Yeah, we can see it.
Okay, so this was kind of the sequence that we were looking at before, I think. And so to go from this is postfix. To go to postfix from I don't remember what this was supposed to be in infix, I think, and this is just off the dome, so I might totally get this wrong. I think it looked like this, maybe. I think. So this is a question mark. I don't know if it's actually going to look like this. This was just if memory serves. And it might have been, yeah, I might have just totally botched this. So let's, for
That's
now.
right.
Oh, this is right? Okay.
Yeah, that's good, right.
So my method for evaluating if they give you postfix and you want to go to infix, the way that I would handle this is I would take both of these and go to expression tree. So expression tree, and then I would go from expression tree to either post or infix, depending on what your needs were. So let's look at building an expression tree from postfix. So let me give myself some space here. Okay, so if you're given postfix, actually, I need a little bit more space, a little bit more. Okay, so if you're given postfix, you create the expression tree essentially by working backwards and filling in the tree from the right. And so we're going to fill in from the right. I guess for the last node, you kind of just have to do the same thing. It's like not really left or right, but we're going to fill in from the right, fill in from the right. I'm going to switch this to look like this, just so that we don't get confused, because these slashes here kind of make it confusing. Okay, anyways, and then we run into an operand, we run into another operand, we run into another operand, we run into an operator, and then we run into an operand and an operand. So I think this is the correct expression tree. I think if this is wrong, somebody call me on it, because I'm gonna say that this is right. So now let's build an expression tree from infix, and I hope this is the right notation. We can actually prove it in a second if this is right or not. My strategy for building a tree with Infix is essentially you want to look at this equation and figure out how you would turn it into operator operands using parentheses. So what does that mean? I would think draw parentheses around your terms such that you can break it into, you've got some left term, you've actually got your operator, and then you've got some right term. And this process is itself recursive because once you've done this, you're going to break your left term into left operator. So left, operator and right term. And that's going to be, again, right here. And then, one more time in here. So don't worry too much about the formal definition of how you do this. I didn't mean to scare you when I said recursive. That's just like, for anyone who's interested, that's just like a little extra little bit. So essentially, the reason you want to do that is because if you break it into left, operand, and right, then that'll help you build the tree sequentially. So as we can see, it looks like we're going to have our operand here, and then, the left part of the tree, and then the right part of the tree. And then the left is going to become, operator, left, right, so on and so forth. But I think because Infix is it feels so natural for us humans, you're never gonna have to think like, how do I operationalize this? You can probably just do this like off the top of your head. It's what I do. So anyways, as we can see, it's clearly A times B is this left term, so it's gonna be this. And then the right term, it's gonna be C minus whatever this is. So that's gonna be this. And then it's going to be D and E. So I hope these two trees are the same that we just made. It should be the same. So we've got this and we've got this. So if you have the toolkit to go from postfix to expression tree, and you have the toolkit to go from infix to expression tree, I think that's gonna do you a lot better than thinking, I've got a queue, I've got a stack, right? The algorithm for like actually doing this, using like data structures is really tough. So if you want to do it by hand flawlessly, do it this way. Okay, so once we've gotten to the expression tree, this is like the key. This is like the key that unlocks every possible notation. So assuming
Could you go over how you got from the postfix to the expression tree again?
Yes. So to get from postfix to expression tree, you essentially fill in, so you start looking at this last element, and then you're going to look at elements from right to left, and you're going to add to the right until you get to an operand, and then that operand will force you to move left. And so if we take this one at a time, we're going to start looking at multiplication, and then we're going to, from left to right, look at our terms. So the next thing we add is subtraction. And as you can see, we fill in the tree we try to stay as rightmost as possible. And as it'll become clear that eventually we're going to be forced to move and fill out the tree to the left when we hit operators. So we do this, and then the next term we're looking at is division. And see, we can still fill in the tree rightwise because we're still looking at operators. When we get to an operand, as you can see, we get to E. This is going to force us to move left because one property of an expression tree is that if we look at the expression tree, one property is that the leaf nodes are all operands, and the internal nodes, including the root, oops, what did I do? The internal nodes will always be operators. So knowing that about an expression tree will let you know that, okay, well, if I reach an operator as I'm traversing this, that's going to force me to move left because you can't have like once you've reached an operand, you can't keep adding operators, right? Because this must be a leaf and these must be internal. So that's just a, you know, intuitively you would kind of pick that up by staring at this for a long time, but it's good to just like, you know, consciously be aware that the operands will always end at the leaf nodes of the tree and the operators go in the middle. So what I just drew, that could never happen. So we added E, and then now let's add D. So D is here. We're filling as rightmost as possible. And then we're going to add C, which is going to be this. So it's going to be here. And then we're going to add another operator and B and A. And as you can see, this tree, this expression tree is valid because we've got our internal nodes are all operators, and then our leaf nodes are all operands. So does that kind of make it, does that do a better job explaining?
Yeah, that does. Thank you.
Okay, yeah, cool.
Hey,
Y'all,
Simon,
yes,
could I actually just make a comment on this?
yeah,
So
please,
could you
please.
scroll up just a little bit so you can see the whole like postfix thing as well?
Yeah.
As well as the tree. Yeah,
Yeah.
so once you write this out, you should be able to follow a postfix like Euler, Tor, Traversal and see that you get the same postfix expression. So like if you want to know that you wrote the correct thing afterwards, just to check, you could follow looking at the postfix going from the right node or whatever. So say he's drawing that out. After you're done drawing that out, you could start, yeah. So you would go and you would follow, yeah, he's got it.
Keep talking.
So if you follow the right side circles, I guess, yeah, one there as well, starting at the root, then you should kind of build this pathway that traverses every single node in a unique way. And if you don't know that, you should know that for your exam, just Euler, Tor, Traversal, or post-order, pre-order, in-order traversals. But if you follow that, you should see that you get the same. So that's just one way you could verify. I wanted to make note of.
Yeah. So, while the stack and the queue method, those are good. Like, you know, maybe if you were trying to actually program this and implement it, when doing it by hand, the Euler tour definitely gives you this. It gives you this extra layer of safety because if you build the tree using infix or postfix to get this expression tree, you can then evaluate the tree 2 times and get infix and postfix right next to each other. And that's like double checking your work, right? So when we get to after this, I'm going to spend some time on tree traversal. So if you're not comfortable with what I just did, I will explain this in just 1 second. So if you do a post order traversal on the tree, you end up getting the postfix notation. And if you do an in order traversal on the tree, you get the infix notation. So I will talk about the Euler tour in just a second. Intuitively, to do an infix evaluation of a tree, imagine you've got like some number line here on the tree, and each node is going to have some position on this number line. The in-order traversal is the easiest one in my opinion, because you can just think of bringing all of these nodes down to this number line, like if you were to flatten them, like horizontally, then as you can see, they would appear in the in order. Plus C minus D divided by E. And as you can see, you know, we have to add some parentheses to preserve the order of operations, which if you were being rigorous, you would add parentheses every time you ran into an operand. For the purposes of this class, you can probably just wing it, which is going to be C minus D divided by E. And let me actually move this down. So I think these should really just drive this point home. If you do your expression tree, then you should see your infix and postfix at the same time. And this is infix. And these 2 expressions match the same tree. They match. So this is how you should handle these questions, I really think. You know, maybe learn the stack method out of curiosity. The stack and queue one is really hard to stomach. But yeah, if you're given a postfix, infix, make your expression tree, do your traversal of that expression tree, and you'll get your notations. Okay. Any questions?
To know, oh, sorry. Will we need to know like the stack method, because in the test 2 topics it said that like using the stack method solve this postfix form.
Okay, I guess it wouldn't hurt. I guess it wouldn't hurt. So if you've got so the stack method is postfix to infix. So if we're looking at this, I'm just gonna rewrite this here. So you've got A, B times C, D, E divided by plus. So the stack method, let's define our stack right here. Let's actually draw this out. So the stack method is going to look something like this. And the rules that we said before are you're going to push operands, and when you get to an operator, actually I'm going to write that out here. So operands, you're going to just push those, and operators, you're going to apply to top 2 elements in the stack, and you're going to push that result. So if we were to do the stack method on this equation, you can see first we run into A is an operand, so we push. We run into B, and now once we run into this multiplication, what did I say? We apply multiplication to the top 2 elements and push that back. So applying multiplication to A times B would give us this. So we pop these from the stack and push the result back. So A times B. And let's continue. So we run into C, which is an operand, we push. We run into D, operand, we push. We run into E. When we get to division, let's see, we apply that to the top 2 elements in the stack. So let's go ahead and apply that. That's going to give us D divided by E. And let's push this result back to the stack. And then we run into another operand, which is going to be subtraction. So let's apply subtraction to these elements. So it's going to be C minus D over E. And then let's pop those from the stack and add this result back, which is going to be C minus D over E. And then one last time is going to be addition. So it's going to be this. So A times B plus. And as you can see, we have traversed this whole operation thing, and we have now ended with the result in our stack. Cool. Is that everyone comfortable with that?
Yes, thank you.
Cool, of course, yeah. And the example on the slides used they used like actual numbers instead of these variables that I have here. And if you were using numbers, then you wouldn't have to keep track of this whole like nasty term, because you would have like actually simplified it. But yeah, that's the stack method. So this is a good segue. The only reason that postfix and infix is easier with expression trees is expression trees as a concept, I think, are pretty fair game, pretty simple. So just as a review of expression trees, or any tree traversal for that matter, imagine we've got a tree with set of nodes. And for this example, I'm going to give you actual like numerical nodes. So I'm going to call this tree traversal. I'm going to give you actual numbers here just to really nail it. So assuming we're looking at actual numbers, and this is a valid binary search tree, let's see, me not run out of room. Okay, so if you're given some kind of valid binary search tree like this, and you're asked for the traversal, what the traversal means essentially is where is the order of the function call relative to the recursive calls. So I know that is like a lot to unpack in that definition, but for instance, if we were to define our pre-order function, so define pre, and we call it on some node, that's going to look like this. This function is going to look like the print or whatever function call you need for that node, and then pre left and pre right. And so those of you who have taken 222 should be able to intuitively kind of see that if we've got one function call, so this is our function, and this could be anything, and then we've got two recursive calls. So I botched that. And we got two recursive calls. There are three permutations of the ordering here, right? We could either have like function recursive recursive, we could have recursive function recursive, or we could have recursive recursive function. And respectively, this is going to be pre-order, in order, and post-order, depending on what order those functions happen in, right? So actually, I'm gonna leave that because that was good. So let's just walk through a little stack example. So if we called pre-order print on this tree right here, then what we're doing essentially is we're saying, so pre of 10 is first we're going to print 10, and then we're going to handle the recursive call to the left and handle the recursive call to the right. So it's going to be pre, and what did I say we're on the left and right? 5 and 20. So this is what the stack is going to look like, the recursive stack for actually calling pre-order traversal. As you can see, first we do our function call, and then we apply the same function to the left and to the right. So in this case, we would do our function call, which is printing 10, and then we would call pre-order on 5, and we would call pre-order on 20. So to call pre-order on 5, we would have to print 5 and then call pre-order on whatever's left of 5 and whatever's right of 5. So in this case, it's going to be 1 and 7. And for 20, it would be printing 20 and then calling pre-order on whatever's left and right of 20, which in this case is going to be 15 and 25. And so the aha moment, and you know, like obviously, right, the order in which these things happen is important, right? So first we're going to print 10, and then we're going to print 5, and then so on and so forth. The aha moment that I want y'all to get out of this recursive stack, and I didn't leave myself enough room, so this is not finished, this is incomplete, but the big takeaway here is that depending on the ordering of your function call and your two recursive calls, that's going to change the order in which the function call happens, right? So inside this recursive block is a bunch of function calls, right? You're going to have a bunch of print statements in here, a bunch of recursive calls. And so if you were to move this function call in between these two blocks of code, that's like saying all of these print statements happen, and then I print 10, and then all of these print statements happen, and then I'm done with the function. Or likewise, if you were to say, I'm going to move this function call to the end of these two blocks and have it down here, well, that's like saying I'm going to print all of these things, and then I'm going to print all of these things, and the last thing that I'm going to do is print the first node. So that's just one little quirk of post-order traversal, is that the root node will always be printed last, because all of the recursive calls have to happen before you get to your function call down here. So let me just give you an example. So if you're looking at a tree like this, if you did post-order traversal on this tree, what's the last thing that you're going to print? Well, it's going to be the root node. And as you can see, when we actually do the post-order traversal and get the postfix notation, the root node is the last thing that we print, in fact. So that is just some background. The test will probably ask you certain questions like, given pre-order, given in order, given post-order, like think of what are some applications of these functions that are actually useful, right? Like when would you use pre-order? When would you use in order? When would you use post-order? Specifically, it depends on how you want that relationship between the function call and the recursive calls to be, right? Like if you are copying a tree, for instance, you need to do pre-order, right? Because you need to do that function call before you can do the recursive calls, because if the function call is like allocate space for a node, so let's say you allocate space and you've got a copy of your tree over here, you allocate space for 10, well, you have to do that before you can allocate space for 5 and 20. So the function call has to come first. So you have to do pre-order traversal. Or likewise, if you're destroying a tree, and let's say, we're destroying this tree that we've got here, you have to do post-order traversal because specifically you can't just delete 10 and then handle your recursive calls, right? Because now the rest of this tree is just gone, it's just floating there. So if you're doing like clearing a tree, which y'all saw in the PA, you have to do post order, right? And post order is like saying you only do your function call once you've done all of your recursive calls. So you only delete 10 once you have done all of the recursive calls and you know that all of its children are taken care of. And then, maybe a good example for in-order traversal is this little property that I was talking about before, is the fact that you can just kind of bring everything down on this number line, and this number line actually sorts everything. So this output will be sorted order. That's guaranteed. Let me just do a little example of that. So I think a tree before, and I might change this a little bit, so forgive me if it's not verbatim, but I think it was like it was like this, something like that. Yeah, I don't remember exactly what it was, but so if you've got a tree like this, and then again, in order is I think the easiest because you can just kind of like flatten it and bring everything down. If you were to do that on this tree, you would see that we have now returned the list in sorted order, which is super useful if you were trying to, if you've got like a binary search tree and you want to see all of the elements in sorted order. See, this is sorted. So be prepared to answer these questions of when you would actually use these things. This is kind of like a little cheat that you can use for in order. Okay, so now that I've got all the talking out of the way, let me explain the Euler tour, which I don't think I've explained before in any of the reviews. So if you've got a tree that looks something like this for the sake of example,